Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm going to tell you a bit about differential dataflow. This is part of a system we've been building in MSR in Silicon Valley with some collaborators. Derek's up in the audience there, and Rebecca and Michael as well. We have a poster in the poster session that's coming up. What I'm going to tell you about now is sort of the data and computational model part of this, which is cool and fun and interesting. The underlying system is also really neat and slightly different, though I'm not going to give you a software stack here and tell you about the different pieces too much. I'm going to try to tell you about the thing that we think is new and awesome and sort of fascinating. Feel free to interrupt if you have questions. I will probably screw up some explanation, but everything should be explainable to just about anyone. In fact, the first slide is going to be embarrassingly simple, and you'll probably be slightly put off. But all right, so here's data parallel data flow, in case anyone wasn't familiar with this. This is not necessarily because I don't expect you guys to know what's going on, but just because I want to get on the same page and get some of our iconography down and get you understanding stuff. So the general pattern in data parallel data flow, as I'm going to think of it, is you have a big collection on the one hand. The collection is then processed by partitioning up the records according to keys. Then each group associated with the key is processed independently, you produce some output results, and they're essentially collapsed together into one big output set. This is exciting. This is basically a primitive MapReduce style step here. People have been using this in big data land for a while, of course, because the independence that's described here lets you partition the computation across lots of machines. We're going to see other reasons that this independence is important, in particular with respect to incremental and efficient iterative processing. But basically, what one of these data parallel data flow things is a certain type of computation that I'm going to describe with an edge. There's a little arrow from one collection to another, and there's some logic associated with the edge that I'm not going to talk anymore about at the moment. All right, so we had MapReduce that said, here's how you do one computation from a set to another set. People moved along from there and came up with more general directed acyclic graph frameworks where you might have multiple collections. You describe the entire computation as a big graph. This is useful for the execution environment because it knows what you're going to do with the outputs of each of the computations. It can do some optimization between the different arrows, lay out the data slightly differently, fuse things together if it needs to, that sort of stuff. Several people then observed that it wasn't strictly speaking necessary to actually have it be acyclic. You could certainly put cycles in there if you wanted. Nothing's preventing you from running some of these edges multiple times, producing new input, rerunning some of the output edges. You need a little bit of help potentially to understand when you should stop. Right? So if you have a cycle in your graph, should you run it 10 times? Should you run it until it stops changing, which could be millions of times or never? So there's a little bit of different approaches people have taken there. I'm not going to tell you too much about the related work there, at least that's not my goal in this talk. So all of these systems that basically do this batch data processing, pick up collections of data, process it, put down a new collection of data, are good. They're good at doing what they do, which is a lot of computation. They're not especially good at certain computational patterns that we would actually like to see, or several people would like to see in these computations. So for example, incremental recomputation or reevaluation. So if I have my terabyte of data, I've gone and processed it, and it took half an hour or so. And someone comes along and says, here's another megabyte. In that half an hour, I crawled a little bit more data, another megabyte. How does the answer change? These systems don't have a story really other than, well, hold on, let me take another half an hour, and I'll go and I'll reevaluate everything for you. Which, that's too bad. We might like to do something incremental. There are systems that have started to do incremental computation, so this is something we should be looking for. Similarly, fixed point iteration or iterative computations where you're expecting the iterate, the collections within the iteration, to stabilize, have the same sort of property that each time you go around this loop, you feel a little silly redoing all of the work from scratch. If only 5% of the data have changed, do you think you might like to push those 5% of changed records through the computation, only do the work related to the reevaluation that you really need to do, and leave everything else stable? And finally, there's this thing called prioritized computation, which not a lot of other systems do, Pritter being a notable paper. This is a little tricky to explain. I'm not trying to do a great job, but the idea is you have these iterative computations where you might like some of the records to actually move through the loop a little faster than others. If they can make progress faster than others, they can preclude some computation that you might otherwise end up doing. And I'll try to give an example in the worked example that we have going throughout the paper, but I might forget. And if so, just harass me about it afterwards, either at the poster or in the question section. All right, so people have built these sorts of systems before. One point, the ideas here are not fundamentally new. Incremental updates, fixed point stuff. Bottom-up semi-native data log evaluation has done this for 30-something years. I don't know. The tricky thing, and the thing that we're going to deal with here, is that these are fundamentally really hard to compose for relatively non-trivial reasons. So if you look at the literature on incremental view maintenance for recursive queries, there's just an explosion of messy stuff all over the place there. The problem being that these collections can change. If you want to do both incremental updates and fixed points, they can change for different reasons, and they're not. You're supposed to do different things in response to the changes for different reasons. And keeping this all sane in your head is just sort of a mess. So one example that I'm going to throw up here, and we're going to work with throughout, this is our motivating example many, many years ago. And it also serves as a great tech demo because it teases out each of these features, and we're going to end up being able to do a relatively good job on it. Think about something like, so take on the one hand all of the big data computations you're familiar with, like grouping things together and then counting them. That's a computation. Think instead about something like maintaining strongly connecting component structure of a graph, like a social graph, Twitter's mention graph, something like that. As edges are continually arriving and departing, we're going to do an example where we maintain a 24-hour sliding window over the Twitter graph second by second. How long do you think that should take in terms of the amount of time to actually compute the correct answer, not a slightly correct answer or something like that, but the actual correct answer? With existing systems, I assert this is in the hours timescale. This strongly connected components uses doubly nested iterative computation, and if you need to start this over from scratch every time, it's a disaster. By the end of the talk, we're going to be doing this in sort of sub-second timescales. So this is, if you want to fall asleep now, great. I'll wake you up at the end when we show the results. You're welcome to do it if you want, but the animations get better. So maybe you should stick around. So I'm going to tell you a little bit about Naiad, it's called Naiad the system. And then after telling you a little bit about Naiad and how it works, I'm going to try to describe the core technical contribution inside it. This is the differential dataflow computational model, which does things slightly differently than a lot of other big data systems. Not wildly differently, but differently enough that it's fun to explain. Just to tell you a bit about Naiad first, this is a data parallel compute engine. It does relatively standard things that you would think of with a data parallel compute system. Data are partitioned up by keys across multiple different machines. We strongly leverage the independence in the subcomputations once we partition the data up. The main thing that's going to be doing differently compared with a lot of the existing systems is it's going to be using an incremental form of data flow. So rather than pushing records around along edges, we're going to be pushing diffs around. We're going to imagine that both endpoints of an arrow are familiar with what the collections were in just a moment ago, and they're really going to communicate what's changed. So this is going to allow us to send a lot less data around. The differential part of the data flow, this is sort of a incremental data flow plus. So we're going to do something slightly different than what traditional incremental approaches to data flow do. That's going to allow us to generalize to this weird arbitrary combinations of loops and iterative updates. I'll show you some examples, but there are a few sort of nice properties that we think they're nice. Anyhow, Naiad has, it integrates really nicely with C# Link. You could use your favorite other language if you want, so we're not trying to make value judgments there, but you don't have to have some new language that blows people's mind or anything like that. Has all these nice features, and importantly is fully composable, so you don't have to go and pick a different system if you want to do loops or if you want to do streaming low latency computations. All of them fit together. Also, relatively excitingly, all of the performance optimizations compose pretty well. So if you want to do an incremental update to an iterative computation, it's not, you could pretty easily imagine that you could get the benefits of either incremental updates or of iterative computation. You end up getting the benefits of both, and things go really, really, really fast. The main trade-off, so that people aren't confused and worried that I'm just trying to sell you a lot of hardware, we're trading a lot of memory for performance. The idea is that when we do these incremental data flow computations, more so even with differential data flow, we're keeping a lot of information about previous computations, stuff that we've already done in the past. We're going to keep this resident in memory so we can quickly get to it and pull it out as required. And as we go through our experiments, I don't have any plots for these things, but memory is going to be the restricting resource. So I think it's correct with industrial trends at the moment that memory prices are going in an absolutely delightful direction. And our machines, which currently have 16 gigs because they were built in a different millennium, can now easily be replaced with things that are, have hundreds of gigs on them. They're just a few $1,000s. So we're sort of comfortable with this. Maybe it's the wrong decision, but it's the decision we made when we went with the system. All right, I'm going to show you a few pictures about using Naiad and what a computation ends up looking like to motivate the differential dataflow computational model. This is largely pictures, so hooray. So we're going to start out, a programmer writes some declarative program in the language of your choice. I've just drawn a picture up here with a few things like relational join and union and a min operator to suggest that you don't really have to commit to a particular language. I'll show you the language we use in the next slide. But this is a connected components computation, directed reachability computation. Let me just explain it because it's simple, and we're going to see it a lot throughout the talk. So you start out with two collections, collections of directed edges. So think of these as pairs of integers or something like that. So we have A comma B is in the set if there's an edge from A to B. And we start out with an initial set of labels, one for each vertex, that are initially going to be the name of the vertex itself. So for every vertex A, we'll have A comma A in our set of labels. And the idea of the algorithm, which will make sense, the picture will make sense once I explain the algorithm, I guess, is it's iteratively going to try to improve the set of labels by repeatedly having every vertex announce to all of its neighbors its own label. And each vertex will then collect all the incoming messages and say, let me change my label to be the smallest value that I've seen so far. And if you feed in a symmetric graph here, what will happen is that this will iterate and iterate and iterate until eventually every vertex is labeled with the name of the smallest name within its connected component. And people in different components will have different names because they're all assumed to be distinct in the first place. And hooray. So this is something that will compute connected components for us. And you could certainly execute this in traditional MapReduce style setting, but it would be relatively expensive. All right, the programs in Naiad look a bit like this. They're C# type things. There's this neat link language that if you're not familiar with, I recommend checking out. It's a lot like a declarative language like SQL, except it has a few little imperative bits and a lot of nice C# things like scoping and things like subroutines that allow you to get a lot more modularity than I think SQL easily supports. This is the directed reachability computation that I described. We start with some edges. We run this to get our initial set of labels, which I guess I've called nodes. That's a mistake. We take our set of edges and we pull out all of the nodes that we see in our edge set. We do distinct, and then we do this iterative computation by invoking a fixed point method. This is the new and exciting thing in sort of the Naiad version of LINQ. The fixed point computation, which will take the thing you're seeing over on the right hand side is an anonymous function in C#. So it's a method from X to something. And C# figures out all the types for you, which is nice. But it's essentially saying each iteration, take the collection that you've got so far and do the thing that we described on the previous slide. Join it with the edges, concatenate in the current set of labels. So you want the option to keep your own old label if that's actually the best one. And then do a nice data parallel min, essentially group by aggregate to find the smallest label. So that's the program you would write. It's not super complicated. There are a few lies in that the actual program has a few more little annotations that I've left out, but it's the same number of lines. The lines are just a little wider. Didn't fit on the slide otherwise. All right, so Naiad takes this thing, compiles it down to a nice cyclic data flow graph. It's not exactly this graph, but it figures out everything using, so putting the loops in where there are these fixed point operators and otherwise using the references that are actually made in the program to build edges between vertices. The graph gets distributed out across a lot of independent workers. So every worker has its own view of the whole graph. So every worker is going to independently work on a little fraction of each of the vertices in the computation. What's a little different from other big data settings is that this computation is actually going to stay resident. So it's going to start running out on your compute cluster. Initially, it's not going to have any data. So you just started it up, and you have a handle to both its input and its output. And when you start it up, you register some interest in its output. So you do this up here. You can sort of read the lines here. We've invoked the directed reachability code, gotten a graph back, the result of which is something that we can subscribe to. And the subscribe method, this is a observer pattern. So the subscribe method says every time you produce some new output, tell my handy little function process labels about it. It will do something exciting, maybe print something to the screen perhaps, or write it to disk, or who knows what. And what we do at this point, once we've set up a computation and the response we want to take to it, we run through some input stream. Who knows? This is you're reading stuff off of your laptop's disk or who knows what. And as often as you'd like, you insert new sets of edges into the input. So you basically have the ability to just feed more and more data at your rate. You get to choose how fast you do this into the input of the computation. And each of the epochs of data that you push in, so each time you call on next, a subscribe will eventually fire with the exact changes to the collection of labels that have resulted from the corresponding ingestion of input. Now, Naiad is clever and complicated and will execute a lot of these things concurrently. It can have multiple epochs outstanding in flight and whatnot. But it gives you the appearance of running these things essentially sequentially. You push in some data, it pushes it through the entire computation, gives you the output, and that's what you see. So the programming model is hopefully, although it's distributed and asynchronous and weird, should appear to be as if it were a relatively synchronous problem. All right. So I'm going to tell you a bit about differential dataflow now. If there are questions about the way the system works, probably a great idea to ask us at the poster. We'll have a demo there and stuff like that. I haven't said enough for anyone to reproduce it, which I understand, but just to give you a picture of what the needs are going to be for the differential dataflow problem. So I'm going to start by describing incremental dataflow. The title of the slide will change at about the same time that the new cool thing that happens in differential dataflow comes into play. If I forget to jump up and down and yell at you about that, you'll notice, and hopefully people will look up and twitch their heads and stuff. So incremental dataflow, which is old, it's been around for a while, takes the approach that data parallel operators, which for a lot of systems like, let's say, Hadoop or MapReduce, operate on collections, so big multi-sets of records, they can actually be designed to operate on differences between collections, not just collections themselves. So when we think of a collection as a multi-set, it's a big set of records and counts, so one count for each record. We could just make that count be a delta instead. It doesn't have to be a positive or non-negative integer. It can be positive or negative integer, with the interpretation that as we get more and more data, we accumulate it up. And when we produce new outputs, we should produce the differences that appropriately tweak the output to look like the right answer. All right. Pedagogically, I'm going to start putting green regions around the diffs. The green regions are going to correspond to what are the diffs that I'm currently accumulating at the moment in the slide while I'm trying to explain things to you. And the thing we're going to have to deal with, basically, is what happens to this operator as new diffs arrive. So diffs are going to stream in. We sort of, in the incremental dataflow setting, do the obvious thing. We produce some output diffs so that the accumulated input is now equal to the accumulated output. Since we have total flexibility to pick dy in response to the change dx coming in, it's not too tricky. All right. This goes on indefinitely, basically. We keep receiving new inputs, produce new outputs using the appropriate sorts of rules. And we essentially build up a system that can react indefinitely to these inputs producing output indefinitely. As I've said before, this isn't particularly new. People have done this in streaming systems before. People have also done this. If you think of going off the right-hand side and then through some other data flow edges coming back and arriving on the left-hand side, this is essentially how people do bottom-up semi-native data log evaluation. So you produce some diffs. They correspond to a new output collection, which changes your input collection, changes your output collection. The system keeps iterating, doing work only proportional to the diffs, until the diffs stop appearing for some reason. And that reason could only be that you found a fixed point, essentially, in your computation. The output, iteration by iteration, has stopped changing. It stays the same. And of course, it will stay the same indefinitely. So both streaming, or incremental computation, and nice iterative computation, doing them both at the same time, though, is a little complicated. If you think about what happens if we took, for example, our connected components computation and asked, let's remove some edges. We want to change our input slightly, so we take some of the edges out. What should the consequences of removing some of the edges from our computation be? And it's not too tricky to see that it's really hard to add a diff to the set of labels that causes us to just repair the absence of those edges. Right? So you might have an edge between two nice big connected parts of the graph that was really crucial in propagating labels from one component to another. And if you remove the edge, you've got to go back and track down everything that went across that edge in the past. And so the approaches historically have been, let's just start over. So just blow away all the history. We'll start over. Tough to slightly sophisticated ways of tracking dependence, basically keeping track for every record of its lineage. Where did it come from? Why is it a record in our system now? We're going to do something sort of in between that's relatively simple, in fact, and ends up working quite well. which is the following. So we're going to implicitly we had previously had these versions associated with our records. I had put them on the screen as the first difference, the second, third, fourth, so on, going out to the side. Let's just make it explicit now. So these could be ints, in this particular case, positive or natural numbers, but they don't have to be. So they don't have to be just integers in this particular setup. For example, they could be a little more complicated. They could be 2 integers. So a diff could come along, and instead of just appending itself to the end of our sequence of diffs, it could say, I have a new second coordinate that's distinguished. It's different from the one coordinate we've been progressing with. I correspond to the second epoch of input data, first iteration, in this particular case. So this would correspond to, in the connected components example, where we've figured out a nice fixed point for all these labels, tweaking one of the edges and saying, please try to restart the computation, essentially, without this edge. See what happens. And to do that, we basically run back to the first iteration and say, OK, we need to modify this appropriately. But we can do the same thing with our output. Since we now have this additional coordinate, we can just say, we'll produce a diff that corresponds to this first iteration, second epoch of data. And we do it the normal way, which is to draw a different green rectangle, one that doesn't include diffs that we do have access to. These diffs are really useful. They're going to be valuable in the future. But they actually just get in the way if we're trying to figure out what is the diff we should produce in the output. We have to diff them all back out and then put them all back in again. So it's really annoying. But this process can be generalized. It just continues, basically. These records that we just produced go back around the loop again and return to our inputs. And we produce more outputs, always growing the rectangles in a particular way that ends up looking a lot like integration or discrete integration, if you guys are familiar with Mobius inversion as the keyword that you should be thinking about. I didn't know about it until this work. So this continues, and we develop a new, basically a re-execution of this iterative computation as diffed off of the previous trace, essentially. So it's a nice data parallel way of doing diffs that diff off of traces. We don't have to do complicated trace analysis like you might do in general purpose incremental computation, because we know that everything's collection oriented. But anyhow. It continues, and as before, we now have something that extends arbitrarily in either direction, so we can incrementally update our inputs as much as we'd like, filling out the incrementally reevaluated iterative computation quite efficiently. The general property we need here is a lattice, or a well-founded join semi-lattice, I think is sufficient if people get excited by these distinctions, but I don't think you do. I'm just going to throw up let's see. It works great. So I'll do this slide and then I'll wind down. I think time is pretty much kicked. This is initially going to be a connected components computation on not very big graph, 100,000 nodes, edges are random. If you wanted to use a baseline style system, each iteration we would need to play around with approximately 100,000 labels. It takes 29 iterations, it turns out, in this case. So a baseline system would just be a straight line if we look at the inner iterations going along the x-axis. If you take something like an incremental system, which says, I'll just do as much work as has changed from the previous iteration, you see something that looks a bit like this. Some of the labels start to stabilize. The y-axis, by the way, is log scale. So even though they're not very far apart, that's a factor of 2 or so. There's still a lot of churn, though, at the beginning. There are lots of people who can't figure out whether they want label 5,000 and something or 3,000 and something, even though they're all going to get label 0 at the end of the day. So they're churning and churning and churning. And after a little bit, the label that takes over that large connecting component dominates, and just everyone quiets down. So that's nice. It's not particularly new, as I've said. So if you come back and change the input graph for some reason, and there's a very good reason, in fact, which is that if we want to do the strongly connected components computation, directed reachability is a sub-computation in that. Basically, if you do directed reachability and you find an edge where the labels on the endpoints of that edge are different, that edge is not in a strongly connected component. It's not too hard to convince yourself of that with just a little bit of head scratching. We can do the head scratching after the talk. But if you run this in the SEC style example, you come back and you change some of the edges. You rip a bunch out of the graph, but you basically need to rerun the computation now, the directed reachability again. And it takes a little less time, not so much less at this point that we would be delighted. There's probably a lot of overhead, sort of bad news. But okay, so we do the directed reachability again. We need to rip out a few more edges now. And this is where it gets a bit more exciting. So the third time around that we've ripped out some edges, this is the amount of work that we need to end up doing. And this is nothing, essentially, compared to all the work we've done previously. Whereas a baseline system, of course, is going to need to go and redo all 100,000 operations. Moreover, this actually ends up taking 9 outer iterations to do SCC properly. And as you can see, once we're done with the second one, essentially, we're more or less done with the entire computation. Everything else just happens more or less instantaneously. And this is really nice. Basically, the few edges that we're cleaning up at the end that aren't technically within strongly connected components, but do influence the computation, we're able to track what are their implications, fix all that stuff up really quickly, and not worry about any of the issues there. It's pretty much, yeah, Jean Grant says I'm done. Great. SCC is wonderful. I'll tell you about it more in the poster session if you're interested, or Derek can tell you about it. That's the code. It runs really fast. This is actual sub-second latencies maintaining the SCC structure of the Twitter graph. Twitter mention graph, sorry, I should say. People talking at one another. And let me just wrap up then. So differential dataflow is this neat, I think neat, sorry, you guys decide for yourself, but neat computational model that allows systems like Naiad to go and do essentially these incremental and iterative computations a bit more naturally, where I think of naturally as only doing the work you really need to do. So it figures out and does a better job of managing the previous work that it's done by allowing you a bit more flexibility in terms of defining previous. Right? So instead of just the collection mere moments ago, you have this logical notion of previous that's general enough to support sort of multidimensional, multiple reasons why a collection might change. Empirically, we get a bunch of good things, though I haven't actually shown you these, but the millisecond scale updates for these complex computations, stuff like SCC, CC, which if you want to rerun from scratch would be a disaster, actually can get updated really quickly. Something that I think is really cool, these last 2 sort of points here. With SCC and some things like it, graph coloring and a few other exciting things, there are these programming patterns you wouldn't necessarily have expected would actually fit into big data computation. If you're thinking about MapReduce and just running a bunch of MapReduce operations atomically over and over again, you would run away from a lot of these programming patterns, nested iterative computations, just as being disastrously expensive. And the efficiency of these programming patterns in differential dataflow gives us the opportunity to do a bunch of things that previously would have been really expensive we just wouldn't have even approached. So a bunch of graph partitioning, graph coloring stuff. Pretty much everything that you can do, I think in GraphLab pretty much you can do in Naiad as a general form of big data computation rather than worrying too much about the specialized systems aspects of it. And we're looking at broadening that too. So if you have problems that you think fit into a nice incremental iterative pattern, bring them to us and we'd be happy to help you figure out, yes, this works great, or no, it doesn't work and we need to fix something in the system. But, I'll wind down there, and if there are questions that don't fit into the questions section, again, we'll just be right outside with everyone else in the demo session. Thanks.